네, 지금 이게 끊긴 것 같죠? 지금은 괜찮으십니까? 그러니까 그전께 끊긴 게 맞나요? 네, 지금은 괜찮고요. 알겠습니다. 그러면은 다시 시작을 하도록 하죠. Okay, this is lecture 16, and I wanted to ask you how about your previous homework? So homework 15. So it was about calculate the transient simulation. So calculate the transient response of your double gate MOSFET. Could you please let me know your status about your homework? Okay, okay. So please go ahead, Mr. Bach. So if you have a question, then please let me know. Mm-hmm. So, so when you say your period is short, how short is it? Mm-hmm. Okay, so then have you plotted your normalized output to your graph? So for example, here we have a time, and time means that yes, here we can say it's second scale. Then if you take 1 second or 10 to the minus 3 second, millisecond, nanosecond, so we will have so many different graphs. So I wanted to recommend you to draw all of them in a normalized manner, normalized time. Then please make a comparison between those graphs obtained from different value of your period. Then if that is or they shows the identical effect, then simply it means that you have not implemented the transient effect. So have you tried this plotting or comparison, or just looking at individual graphs, and since they look quite similar, you say that no transient effect is observed? Okay, then please, I want to ask you to do this job. And yeah, so please try to this job, and if you have still no difference, no, I mean that when I say no difference, sometimes, okay, sometimes it can okay, something happened. So can you hear me? Hmm. Mm, mm. Okay, okay, sorry about that. But I have no idea about what's going on. Hmm. Okay. Wow. Okay. Oh, sorry about that. So I'm now using different. Mm, mm, okay. Mm, 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 mm. Okay. So sorry once again. Sorry about the interruption. Mm, okay. So please check your result. So when you have your simulation with different time period, then you will have also a different waveform. But if time scale is not sufficiently short enough, then it would be very difficult for you to observe the transient effect. But I'm not quite sure what will be the required time scale for your simulation, so I strongly recommend you to make a comparison. So when you make a comparison, I think that these one will not show any meaningful differences, but please make a comparison like this. just check the number, not a graph. So human eyes can be easily fooled by these graphs. So seemingly they look identical. However, if we just open the file and see the number, maybe they have certain differences. Then it's okay. So for example, if you go to here, although graphs looks quite similar, but if the number is different, then please go ahead with your code, further increase your time or your frequency. However, if all of them are identical in its number, it certainly means that your code does not contain any of transient effect. So please try to test this job. Okay. And another thing, you can try is test a homogeneous sample instead of considering uh, a double gate MOSFET, then you may try to test a homogeneous sample. Then homogeneous sample means that you have just a homogeneously doped n-type bar, so you will have certain knowledge on okay, so can you see this PDF file? For example, let's visit the homogeneous sample. Yes, for example. So you can find this paper written by myself, and that paper was introduced or written for transient simulation of semiconductor devices. Of course, in this paper I used deterministic Boltzmann equation solver for our code, but anyhow you can have something. Yes, homogeneous sample at equilibrium. For example, if you are not sure about the functionality of your code, then please try to simulate this guy. So it is just a one-dimensional system, so it would be very easy for you to implement it. So then yes, so after calculating this guy, so you will have something like this. You change the frequency and calculate your y parameter. Okay, so you will have these numbers. So also you can take the analytic solution. So please try to do this job. Okay, mean that there will be two different ways to test your result. First thing you have to do is just to check whether your simulation result is really altered by changing this time scale. So if there is a small differences, then it's okay. So then whether that is really true or not should be tested by this second one, test a homogeneous sample, and in this case the y parameter of your device is already given from the homogeneous sample equation, so please make a comparison. Okay, so do you guys all understand my suggestions? So you can try both of them. Yes, the first one and second one. Okay. Yes, please, Mr. Bach. Okay, so your question is your current does not include the displacement current. So right? So if your current does not include the displacement current, then please include. Okay. So you have already included that component, but you don't understand the equation. So the equation is quite simple. So your total current should be sum of yes, sum of yes, and finally you have to include displacement current density. Yes, and this displacement current density is simply given by so time derivative of your displacement vector. Okay, so this is the form for you to use it. And in the case of our case, the displacement vector is always assumed as this form. Yes, this is permittivity and this is electric field. Also, we have assumed that electric field can be written as gradient of electrostatic potential, of course minus. So we will have this form. Yes, this is the form we will use for our calculation. So think about the time derivative of this quantity. So epsilon is a function of position. However, if there is no change in the material as a function of time, then this can be regarded as a constant over the time. So only time difference can occur through this, this electrostatic potential term. So when you calculate it, then you have to calculate this component. However, at a given position R, it is quite easy to calculate it. So if we just take the backward-Euler method, then we will have delta t as a denominator, and here we have R and R, but evaluated at t equal t sub I and t equal t sub I minus 1. So that will be all for calculating the time derivative of the electrostatic potential. Yes. So Mr. Bach, could you please let me know where is the point you have difficulties for your implementation? Then I can give you further answer, more specific answer to your question. So could you please? Okay, so then I think that today the original plan of mine was to introduce AC simulation capability, but following your questions, I feel that this is not the right time to go ahead, and please concentrate on your second task. So second homework. I mean that in this time. So we will not go forward to the AC simulation. So please test a homogeneous sample. So please try to set your homogeneous sample following my paper, JEDS paper. So you know it. Let me just show it once again. It is shown here. So please take it. And of course, since we are in the institute, so you can easily download it from your site. Then please try to calculate the y parameter. So let me just tell you how can you do that. So if I remember correctly, first of all, you have to build a system, homogeneous bar. So do not come back to the one-dimensional structure. So just to consider two-dimensional structure, and please attach here one terminal and the other terminal. Okay, then from this one, so since the simplest one is related with just equilibrium case, just to say this is the case. I hope that you can immediately get the solution. So what will be the solution? Yes, electron density would be quite similar with donor density. Yes, so you will have this kind of behavior. Potential, yes, potential would be almost, not almost, perfectly constant over your device. So once you have this kind of a system, then what you have to do is now, instead of this 0 voltage applied to the right contact, so please introduce a sinusoidal signal to your right side contact. So any contact is okay, but anyhow, please introduce it. And yes, so for example, this V of t should be have a certain form like a sine or cosine, whatever, and of course it will, for example, let's say this is a sine function, and this is a sine function, and you have omega t, and of course you have amplitude here, and that amplitude should be small enough, for example, point 1 millivolt or something like that. And please change your frequency. So when you change your frequency, then you will have different numbers. Then please perform the simulation, and here you have anode, so you will have anode current, and this is time. So you will have such a graphs when you have a low frequency condition, of course. So you have applied the sine signal and will get also sine signal, because this is just a homogeneous sample. It can be regarded as a resistor at low frequency, so you will have also sine function. Then once you have I or not, then please don't use the first period. Yes, this first period can contain such a transient effect, so I wanted to recommend you to avoid the use of the first few periods. So what is the first few? I mean that how long or how many periods should be skipped before used for analysis? It really depends on your situation. So depending on the case, for example, if you are working with a really low frequency case, then there will be almost no transient effect. Even the first period would be perfectly okay. However, if you have a high frequency case, then maybe you will have a certain intermediate state. So please wait for a while to have a stabilized solution for your waveform. So then now let's assume that you have certain stabilized form. Stabilized form means that, okay, you have, for example, S period, and also you will have S plus 1 period. However, if your solution is really stabilized, then now you have periodicity. Yes, there is no difference. Also, yes, there is no difference. So once after this transient effect is gone, then you have applied the periodic signal, and your response, here response is the anode current is regarded as a response, then this response will be also perfect periodic signal. Okay, so once you get this periodicity, of course you have to check it, then please take okay, then please take this one single signal. After that, from this condition, please try to calculate your y parameter. So y parameter of course contains both terms. So which one is real part and imaginary part, and the real part is the part which is in phase with your input signal, and imaginary part is corresponding to that one which is out of phase with your the input signal. So please try to evaluate this y parameter. Then also you have an analytic means to calculate your y parameter. Then please just handy calculate your y parameter and make a comparison. So in this case, the system is so simple and homogeneous, and your result should be perfectly matched with the identical, also the analytical expression. Okay, so do you guys all understand the modified homework today? So I will say that this is corresponding to your homework in this lecture. Okay, so instead of having other more advanced topic, so in this lecture 16, just to concentrate on the verification of your transient code with a homogeneous sample. Okay, so your calculation or your homework should contain both parts, the two parts. One part is analytic discussion about your homogeneous sample. Then please try to derive the expressions for your y parameter. Of course, that is already done in my paper with a much more general case. So general case means that my analysis takes the time derivative term of j sub n, but you don't have to do it in this homework. Just neglect this term, and just consider the normal drift, conventional drift diffusion 1, and please derive the expression for your y parameter. And now your second part of course so contain your numerical result. Then please make a comparison between your analytic result and numerical result. And if you have done it properly, then at a one shot you will get the perfect agreement. But my usual guess is maybe there is something wrong inside your numerical implementation. Then this homework will give you certain clues to remedy your bugs. Okay, so I think that this is quite good for your test of the transient simulation. Okay, so do you guys all understand the newly generated homework number 16? So please confirm it. And if you have any question on this homework number 16, then please let me know. Okay. Okay. So then I have no intention to extend our uh, lecture progress further. So let me just do this first task together with me. So I'm now saying that how can you calculate this analytic expression for our system. Okay, so up to now we have done many jobs about numerical simulation, but I think that this is almost the first time for us to think about analytic solution of semiconductor device equation. So we have to consider two different equations. Of course, here we have holes. However, yes, for while, just neglect it. Of course, when you implement the numerical calculation, so it is required to include the, the whole continuity equation, but for our simple analytic expression, so just to neglect the holes, then which one should be considered? In this case, so we have to consider electron continuity equation and also Poisson equation should be considered. Okay, then why don't you just write down? So in this case, this is the form we have to use. And how about the electron continuity equation? So say, okay, so let me just change it to partial derivative. Okay. This is in this one-dimensional case. What we have to do is Q. Oh, sorry about that. Round x, j, n. Okay, we need this type of expression, so we need both of them. Yes, and you know that now law should be written as the sum of whole contribution, electron contribution, and doping contribution. However, in this case, we will consider only, yes, electron density and also donor density. Usually we have to consider also holes in it, but in this case holes are neglected. It is okay to say this way. And yeah, also let's just think about the D field. D is displacement vector, and yes, this can be written as this form. Yes, multiply the permittivity multiplied by the electric field, and that can be also written as this form. So when we just introduce this expression, then the form will be look like this. The second derivative of electrostatic potential should be equal to minus Qn plus Qnd plus. Okay, and here we have N, T, and this is corresponding to, yes, and now we have to write down the J sub N. J sub N, yes, J sub N is Q mu N, and and here we have electric field, and Q dn round n over round x. So please don't be confused with the displacement vector and diffusivity d sub n. And here we will write down minus q mu n and round here plus q dn round n round x. Okay, so are you all with me? So if you have any question, then please let me know. Then now we must solve this system. What you have to do is solve these two equations. So of course, what are unknown variables? In this case, we will treat phi and n as an unknown variable. Of course, this phi can be a function of x and t, and also n can be a function of x and t. Then our assumption is now, since we are first considering the equilibrium case, there will be no current conduction, and try to assume this form. Okay, this is homogeneous, and this is at equilibrium. So both of time dependence and position dependence is gone, and let's say that this is just a constant. And also electron density, yes, so in this case we will just say nd plus, yes, let's just call it as n sub naught. Okay, then let's just try this test solution. So both of the electrostatic potential and the electron density are constant, and our first Poisson equation, so Poisson equation, this guy just gives us 0, because please, the left hand side becomes immediately 0, because we are now taking the constant value for our electrostatic potential. And when you go to the right hand side term, then now we have minus q and naught and q and d plus. But you know what is n naught? Actually, that is corresponding to donor density, so we will have 0. Okay, the Poisson equation is automatically satisfied this test function. Okay, so if you have any question, then please interrupt me even when I'm deriving something. So I'm saying that now we have the test function which satisfies the Poisson equation. Then how about electron continuity equation? In this case, please check your left hand side term. So round n over round t is also identically 0, because we have assumed time invariant and homogeneous solution for our electron density. Okay, now it is now given by 1 over n, yes, time position wise derivative of a certain term. But you know that the first term is the drift related term, and it is related with electric field. Electric field Mhm. Okay, so sorry about that. Okay, okay. So can you hear me clearly? So I have a problem related with maintaining the streaming. So could you please let me know you can hear me clearly? Okay. The status of our streaming seems to be bad. So okay, good. Thank you, Mr. Han. So when was the last content you heard clearly? Okay, so Mr. Bak, thank you. And could you please let me know which one was the last thing? Okay, good. So okay, good. So that's not much. So let me just come back to this part. Okay, now you understand. Okay, now you understand the homogeneous solution really satisfies the Poisson equation. And now we will test the electron continuity equation. But when we try to test the electron continuity equation, we immediately find that this is also true for our electron continuity equation. Round n over round t vanishes. Okay, it's okay. And when you go to the right hand side term, the first term is related with the electric field, and electric field is directly related with the gradient of electrostatic potential. But since the electrostatic potential is a constant, yes, immediately we have no drift term. And how about the diffusion term? Diffusion is related with also gradient of the electron density, and since we are assuming a homogeneous quantity, so both of them also vanish. Okay, so from this consideration, now we can say that this phi equal to phi naught and n equal to n naught, both of them are equilibrium quantities. This satisfies the Poisson equation and electron continuity equation at equilibrium. Okay, so this is the starting point of our discussion. Okay, do you have any question about this solution? Okay, I'm afraid that actually we are experiencing certain difficulties to maintain the live streaming, but anyhow, I will try my best. Okay. Okay. So now let's go to the next part. So our goal is to calculate the y parameter. So from now on, I will give you how can we calculate the y parameter out of this equilibrium case. So simply speaking, now we assume that phi, which is a function of position and time, is no longer a constant. So this is equilibrium 1. However, we have introduced also this small deviation from our equilibrium value. Also, electron density, which was assumed to be a constant, now modified as containing this delta n term. Okay, so once again, these phi naught and naught, they are homogeneous. So they are just constant over position, but this guy, delta phi and delta n, they can be a function of position and functions of time. Okay, so then let me just insert this test solution into our Poisson equation and electron continuity equation and see what happens to this system. Okay, so if you don't understand any of this discussion, then please let me know. This is directly related with our AC simulation. So let me just evaluate Poisson equation. Now, Poisson equation. Then minus epsilon and second derivative of our phi can be now written as second derivative of what? Just delta phi. Or of course, we have to consider second derivative of phi naught. However, since that is the homogeneous solution, so I mean that does not depend on the position variable, so we will just have the second derivative of delta phi. And let's go to the right hand side. Yes, so q minus qn plus q nd plus, however, this n not exactly cancel out nd plus, so we will have just minus q and delta n. So let me just write it down. When we just insert the test form of phi and n into our Poisson equation, what we will get is the Poisson equation which is valid for this test solution. So it just looks like this. Now we can say that this is just this is the Poisson equation which is valid for our delta values. So delta n and delta phi. This is originated from what? From the Poisson equation. So if you have any question for my derivation, then please let me know. Understanding this concept is fundamentally important to further advance with the AC simulation. So please, if you have any question, then let me know. Then let's change my color to different one to show the difference. Yes, now we will move to electron continuity equation. Then let me just insert it. Once again, the left hand side term gives us what? Gives us round delta n over round t. Of course, once again, we have to evaluate the time derivative of equilibrium solution, but that does not depend on the time variable. So only this delta component will show the time derivation. And when you go to the right hand side term, now we have a lot of terms here. So let's just think about this. Here, yes, minus q, mu is regarded as a constant, so just put it here. And now we have n naught plus delta n. Also, here we have round over round x, and it has phi naught plus delta phi. And let's go to the second diffusion term, q dn, and also it has n naught plus delta n and round x. Yes. However, when we consider these gradient terms, so we can easily find that this does not contribute at all, and this does not contribute at all. So we can get this expression. One thing we have to keep in mind is this delta n and delta phi are regarded as small quantities. So multiplying these two small quantities, that will give us really a negligible quantity. So what happens? For example, when you have a look at this part, we have n naught plus delta n multiplied by round delta phi over delta x. You know that this is a small quantity, and this is, yes, this is not a small quantity, and this is a small quantity. So multiplying this and that will give us the second order expression. So we will not keep it at all. So simply speaking, in order to keep our expression only up to the first order, then we will simply neglect the term in here. This is the only way for us to keep our equation up to the first order. Okay, so now that's it. So this is the electron continuity equation written in this case, in this homogeneous case. Then let me further write it down. Yes. So now we have to evaluate this partial derivative, but you know that here q, mu n, and n naught, all of them have been already regarded as a constant, so we will have simply minus q mu n, and not all of them are constant, and just taking second derivative of your delta phi. So that will be the first term originated from the drift term. And how about the diffusion related term? This term also gives us quite much simplified form. So qdn, and we will have just second derivative of what? Second derivative of delta n. Of course, you know, here q and 1 over q can be cancelled out each other. So yes, this guy gone here, and also 1 over q, they are cancelled out to each other. So we will have much simplified form shown here. So this is the electron continuity equation, and this is Poisson equation. Okay, so are you guys all with me? So then let me just solve this expression in the frequency domain, not in time domain. Of course, I wanted to say that this form, the Poisson equation and the electron continuity equations, which are boxed here, this guy, and this guy, are valid in x and t domain. Yes, so as much as delta n and delta phi are kept as small, then we can even consider arbitrary shape. For example, your voltage excitation can be function of time. You can apply this step like excitation to your anode contact. That is allowed for this time domain expression. However, let's assume that instead of this quite much general expression, you are now just applying sinusoidal signal. Once you apply the sinusoidal signal to your system, then it is expected that also your response will be sinusoidal, so you can make the frequency domain analysis. So that's the reason why instead of this time domain expression, so from now on we will just transform our equations into the frequency domain. So it is quite easy to perform this transform. So let me just write down here. In the case of a Poisson equation has no time dependence. So it is not converted, or it does not change its form. So Poisson equation here is regarded as just instantaneous term, an instantaneous equation, so we can write it down here. So however, although I have used the same notation, delta phi and delta n, in this part, this delta n cannot be regarded as this time-dependent quantity. It should be regarded as function of x and function of omega. Also, this delta n should be regarded as a function of x and function of omega. Already that is transformed into the frequency domain. And how about electron continuity equation? In this case, now we have time derivative term. So this time derivative operator is now changed into j omega in the frequency domain. So now we have j omega delta n. However, please note that we cannot say so. J omega delta n, which is function of time, function of position, and function of time. No, it's not possible. It's already because we have assumed that we are now working in the frequency domain and we have converted the time derivative operator into j omega. That is always only possible when we consider the delta n, which is shown in the frequency domain. So we will have x omega. Okay, then the remaining terms are just all instantaneous, so we can just write down in this way: second derivative of phi, and now you have dn x and delta n. So these and these are two equations we will use to calculate the analysis of y parameters. So I think that I have already shown you how can you start your analytic analysis, the analytic discussion. Then your delta n and delta phi will satisfy this form. Of course, you have to specify the boundary condition, but in this case, please use this form. So delta n x equal to 0, the left contact is always 0. And delta n and x equal to L, which is corresponding to your right contact, that is also assumed to be 0. And how about potential? Yes, the left contact x equal to 0, that still gives you 0. And finally, delta phi at x equal to L, the potential fluctuation at the right contact should be regarded as your V amp. Okay, then using these 4 boundary conditions and 2 equations, so you can get the solution for your system. So this is the first part of your homework number 16. So please try to solve this equation and get the expression for your y parameter. Of course, once you get the delta phi and delta n, then from that quantity you can calculate also the, okay, so what happens? You can calculate J sub n, of course, together with the displacement current, so that will define your y parameter. Okay, so today we have had quite much difficulties to continue our live streaming, so I'm not so sure why we have such problems, but anyhow I have explained the analytic ways to calculate the y parameter. Okay, so I see that the time is up, so please try to test your already written code with homogeneous sample, and please improve your skills, analytic skills to analysis your system. Okay, do you have any question about homework number 16? So please confirm everybody has understood the homework number 16. Then I will wrap up today's lecture. So if you have any additional question, then please use our direct message. Okay, Mr. Jung, thank you. Okay, good. Okay, thank you for participating this lecture. And of course, this Thursday is the Children's Day, so that is a national holiday. We will not have any lecture at all. So let's see you 1 week later, and please try to solve this homework number 16. Once you have solved this homework number 16, then um, please test again with your double gate MOSFET example. So you will have better result, I hope. Okay, see you next week. Bye.